Okay, so today we want to discuss the Aharonov-Bohm effect. But before doing that, let me talk about, give a comment or an observation about the energy levels of a charged particle when a magnetic field is turned on. Okay, so I'm being a little bit ambiguous intentionally. So before we do this, let me just tell you that what we are going to do, but the first treatment we are going to do using Schrodinger equation. But the treatment of Aharonov-Bohm effect is going to be using path integrals. But we could have used Schrodinger's equation and the Schrodinger approach to derive the Aharonov-Bohm effect. And in fact, that is the approach that Aharonov and Bohm did themselves. But I think that this Aharonov-Bohm effect is a very nice illustration of how to think about the path integral. And therefore, instead of using the Schrodinger approach, I will use the path integral approach when it comes to the Aharonov-Bohm effect, okay? So our preliminary system, suppose we take a very long coaxial cylinders, okay? So we have a cylinder and like this. So it's very long. So we want it to be long so that we don't have to worry about edge effects. And this is the inside cylinder, and there's an outside cylinder. And in between, there's an empty space. Okay. Now suppose that, so the walls of the cylinder are impenetrable. I don't care what they're made out of, but they're impenetrable walls. By impenetrable, I mean that if I put, say, a quantum particle in one of these cylinders, they won't be able to tunnel out. As you know that from the particle in the box, example, which is essentially a potential with infinitely high walls, right? So these are equal, these are similar, but the geometry is three-dimensional. And now suppose I put an electron in between the inner and the outer cylinders, okay? So this is an electron, a quantum mechanical particle. Okay, so is the setting clear? Okay. So then we have two situations. In one situation, there is no magnetic field. By the way, let me call the radius of the inner cylinder rho A, and the radius of the outer cylinder, say, rho B. Okay. So one thing you know is that the wave function of the electron must vanish for the polar coordinate rho less than rho A, or equal to, right? Why is this?
Because the walls are impenetrable.
Right, exactly. And it will also vanish for, you know, for rho bigger than B. But but we are not really interested in the other one so much, and because we'll see. Okay. So now, situation B. Okay, before we go to the second situation, what can we do? We have, not in this course, but in a previous course, we solved the Schrodinger equation for a particle in a box, right? So this is also a particle in a box with an interesting geometry, right? So using the same technique and using this boundary condition, we can solve the Schrodinger equation for this for the energy level of this electron, right? Now, even though it's a charged particle, for the, what we have to solve is essentially the free Schrodinger equation with this boundary condition, right? Because there is no electromagnetic field. And therefore, if I look at the Schrodinger equation over here, this term would be 0. And this is also 0. And therefore, this just becomes the free Hamiltonian, because there is no electromagnetic field in this region. So this is going to be the free Schrodinger equation. Is that clear? Rahul?
Um, and could you come again? I cannot.
I mean, is this clear that why we have to solve the free Schrodinger equation?
Uh, Not really.
Okay. So can someone else explain why we have to solve the free Schrodinger equation in this case?
Because we still don't have any electromagnetic fields here, so there's no potential.
So, there is no potential. There's an electromagnetic field. So the only thing that is different from a free particle is that it cannot escape from this region. It cannot go out or it cannot go in. And that is taken care of by this boundary condition that psi must vanish for rho less than rho a and greater than rho v. But apart from that, the equation is the free Schrodinger equation. In physics, a differential equation does not live in vacuum. Well, also in mathematics. A differential equation, its meaning always depends on what boundary conditions you impose on it. So the energy level that we are going to get for this system will depend on this boundary condition. So, let me just remind you very quickly what we did for the particle in the box. So the particle in the box is, we had a box which had infinitely high walls. So this was a one-dimensional system, and this went all the way to infinity. This is the potential, and this is x. Suppose this is the origin, and we had a particle in the box. But because it had an infinitely high potential, we knew that the wave function could not leak out. So the wave function had to go to 0 at the boundary. So the wave function could be of this form. It could also be of this form, or it could also be of this form. And these were the these were the only allowed wave functions. And it's very easy to solve the Schrodinger equation using this restriction. And if you use this restriction, you can show that the solutions are essentially half sine wave or half cosine wave. Well, not half necessarily. Sine waves or not waves, sine functions or cosine functions. And because of the boundary condition, there is a restriction on the energy levels. And the energy levels, do you remember what the energy levels look like? What were they? If n is an integer, say 1, 2, ... What did they look like? Do you remember?
So it's proportional to n square.
Exactly. Yeah. And similarly, if you looked at, say, but this was the free, but we did a free. This was a free particle. Well, this was not a free particle. This was we solved the quote-unquote free Schrodinger equation in this region with this boundary condition. Okay, so we are doing the same thing here, but in higher dimension. And therefore, we can solve the Schrodinger equation, and it'll give me some discrete spectrum of energy eigenvalues. And does that make that a bit clearer, the analogy?
Yes, sir. Yes, sir.
Okay. So this is situation 1. Situation 2 is going to be, we are going to turn on a constant magnetic field in region rho less than A. Okay, so what we're going to do is that we get to now turn on some magnetic field such that the magnetic flux lines will just go like that. Okay. But we are going to design our magnetic field in such a way that it only stays in the inside region, the inside cylinder. Okay? Now we're taking it constant. It doesn't have to be constant, but let's take the simplest case. So this is situation 2. Now let's see what kind of vector potential does this give rise to. Now classically, if electron was a classical particle, classically, B, since B and E doesn't change, since B and E don't change, a classical particles, say energies, or energy, will be completely unaffected, right? Do you agree? Suppose you're sleeping in a room, in a soundproof room, and somebody starts shouting outside the room. But since your room is soundproof, will your sleep be disturbed?
No, for a classical sleep.
Yeah, for classical Nahi, his sleep will not be disturbed. Now let's see what happens to quantum Nahi, okay? Or quantum Rahul or quantum moon, okay? Okay, so to do that, we have to find out what kind of gauge potential gives rise to a magnetic field B, which has the form that it is some constant times, say K, inside, that is rho less than rho A, and it's 0 outside, right? That is rho greater or equal to rho A. So this is the magnetic field we have. We have to find out what the so let's look at it. We can solve it. We can solve the B is equal to curl of A equation, or you can just check it by plugging this in. And so the solution is that A inside will be the constant B times rho divided by 2 phi hat. What is phi? Phi is the unit vector in the azimuthal direction. So we are using cylindrical polar coordinates because obviously this system has cylindrical symmetry. We should always use the coordinate system that is designed for that symmetry. Makes life a lot more easy. So this is inside. Outside, now the gauge potential should be, it should be continuous. So it should match on the walls. So outside it's rho B, rho A squared divided by 2 rho phi hat. Okay? And as you can see, A so let's call this out. Let's call this in. A outside at rho equals to rho A is equal to A inside at rho is equals to rho A. So they match. So it's a continuous. Now, how do you find B? Well, B is curl of A. And in cylindrical polar coordinates, the curl operator is given by rho hat, this is the unit vector in the rho direction, divided by rho. Phi hat, this is the unit vector in the azimuthal angle direction. K hat or Z hat divided by rho. And then d by d rho, d by d phi, d by dz, acting on A rho, the rho component of the vector potential, rho times A phi, A of Z. And this is something you should learn in your vector calculus course or tensor analysis course. And I'm not going to go into detail here. I encourage you to go back and look this up in the curvilinear coordinate part of your vector calculus course, okay? Now, in this case, the only non-zero component of my vector potential is this. And we kind of know that, this is the only one that's going to give rise to the magnetic field. So if you calculate this, we just get K hat divided by rho and then we have d by d rho, which is this derivative, and then rho times A of phi. Now let's calculate this. We have K hat by rho, d by d rho, then, let me do this, rho. And what is A phi inside? A phi inside is B rho by 2 inside. Outside is B row A squared divided by 2 row. Now, if I'm inside, then I have K hat, and then you see that hang on. Yeah. So if I'm inside, then we see that it's D by D row, then B row squared by 2. So we get, what do we get? We get B row. And there is a row divided by row here. So if I take that inside, sorry, let me just put the 1 over row here. So there'll be row. And then we just get B, right? So this is inside. And if you're outside, then D by D row. Inside we have, because of this factor of row, that is multiplying A of phi. So we have a row. What is A of phi? A of phi outside is B row A squared divided by 2 row. So we see that there's a cancellation here. And therefore, the derivative is acting on a constant quantity. So we get outside. Okay. So we have satisfied that, this configuration of the gauge potential gives rise to a constant magnetic field inside and a 0 magnetic field outside. Okay? So now, suppose that we take a disk of some radius. Suppose we take a disk like this. So the disk its radius is somewhere in between, say, row A and row B. Let's call it row prime. And so this disk encloses an area, and let's call this surface sigma. Okay, are you clear of what the geometry is? It's an imaginary disk. It's okay. And now we want to calculate the flux through this disk. So the flux through this disk is the B dot dA, right? Now, using Stokes' theorem, okay, first we can write B as a curl of A, dotted with B of A. But we know using Stokes' theorem, let me draw this picture again. This is my sigma, and B is going in this direction somewhere. B becomes 0 at some point. So by Stokes' theorem, sorry, I don't know what happened. Yeah, we can write this surface integral as a line integral on the boundary. So the boundary is here. This is the boundary. I'm calling this boundary of gamma. And by Stokes' theorem, it is A dot D of S, or I don't know, X. Yeah, let's call it S. Okay, where S is, it's a tiny bit of loop on the boundary.